Chapter 1, Whole Numbers. Section 1.1, How the Whole Number System is Organized. Okay, let's look at how our system started. We have the Arabic numeral system. That means that we use certain symbols to represent quantities. So, based off our textbook, we call them digits. I'm going to put in parentheses symbols because that's technically what they are. They're symbols that we use to represent quantities. The symbols, digits that we use in the Arabic numeral system are these. We use these 10 digits to make all of our numbers in the Arabic numeral system. Now, these are just the digits or symbols. They have no meaning until our system gave them some meaning. So in this case, let's look at this one for example. This is just a symbol. It could have been a rock or a tree or some other symbol in another culture. For us, in our system, this represents this quantity. This one here, for example, same thing. It's a symbol and it happens to represent this quantity in our system. So we use these digits or symbols to build numbers. I want to start with the base number system. The base number system are the natural numbers. The natural numbers are 1, 2, 3, so on. These were the base numbers that we used in our system. They represented the quantities that we showed earlier, 1, 2, etc. The whole numbers actually build on this set. The whole numbers are the natural numbers plus 0. We added, in our system, we added in this symbol here to represent the absence of a quantity. So this was the absence of a quantity. This is the absence of a quantity. So 0 represents nothing. Previously in our culture, they would just leave a blank space if there was nothing there. And later on, they used this symbol to represent the absence of a quantity. Alright, so this is our whole numbers. I'm going to just draw a little picture here. So if this is the natural numbers, the whole numbers contain the natural numbers. And we'll build on this graph, by the way, as we go throughout the course, because we'll deal with other number sets. For right now, we're just going to be dealing with the whole numbers in Chapter 1. Okay? Alright, let's look now. We take these digits to form numbers. Let's take two of them. Let's take these two digits here, and we form a number. So in our system, this has meaning to us. Specifically because of a concept we call place value. I'll ask students, I'll point to this in class and say, hey, what number is this? I have students tell me this is the number 2. Is that correct? No, in our number system, because we have meaning, because of place value, that number is actually 20, not 2. Now it's the digit 2, but its actual number is 20. If we look at this here, this is 20 plus 7. So that's how we get the number 27, because of place value. So this is a big concept for us here in our number system to get us started. Our number system is a base 10 number system. Now what that means is the place values are determined because we use base 10. So in this case here, this is the ones place, this is the tens place, and so on. Hundreds, thousands, etc. What this means when we say base 10 is if we have, let me expand this number out just a little bit. Let's say we had this. Well, this position here is the thousands place. This position here is the hundreds place. This position here is the tens place. This position here is the ones place. So if you notice, all of these here, place value, we know to be thousands, hundreds, tens, ones. This one here is 1,000 is 10 to the third power. Notice it's a base 10 with the power of 3. The hundreds place is 10 to the second power. Base 10, power 2. The tens place is 10 to the 1 power. Now here's the interesting part. What power is this one? What power is the ones place? Because we know that this makes 1,000, this makes 100, this makes 10. How do we get 1? Well, the power we need here is 0. And throughout the course, if you have any questions, we ask, look it up. I want you to ask questions. Why? Why is that the case? Well, in our system, anything to the 0 power is always 1. And you might ask why? That's a good question. I do some ACT review for high school students sometimes, and it's a great point. You know, on the ACT they'll get you with certain things, especially they get you with concepts, not necessarily that you don't know things, but they get you with concepts. So in this case, why is this 1? Well, let me prove why it's 1, and that should be, you should say why, or we should be able to find a proof for this. Well, there's an exponent rule that says if you divide exponents with the same base, then you can subtract the powers. So in this case here, look, if we had, this would give us 5 sevens, this would give us 4 sevens, which if we canceled the sevens, we have 7 to the 1 power. What that the exponent rule allows us to do is to take this and more efficiently get that result. 7 to the 5 minus 4 is 7 to the 1, so that's how we can get here. So based on this rule, what if we had 7 to the 5 power over 7 to the 5 power? Well, anything divided by itself is always 1. That makes sense. So if we apply the exponent rule here, it says 7 to the 5 minus 5, which is 7 to the 0, which is 1. So anytime you have something to the 0 power, it equals 1, because it means originally you had something divided by itself. This is how we get the ones place, because we had 10 to the 0 power, which stays with our base 10 system. This is going to be an important piece moving forward when we deal with other numbers, specifically decimals, later on in the course.